Okay, so not to the small. All right, so we were going through the different methods. We did concentric, we did trammel, intersecting arcs. All right, true. This is the intersecting arcs method. Let me find a shorter one. I guess that was the shortest one. Anyways, it's just to kind of get an idea of what we're going on here, right? So in section arc, you draw your major axis, you draw your minor axis, and then essentially you're just going to draw a bunch of arcs, right? I mean, it's obviously a lot more than just that, but what you're going to do is you're going to divide some spaces up in the major axis and divide some spaces in the minor axis, and you're going to draw arcs from each of the points. You see the first arc is from the ends of each of the axes. So that will give you focal points. So those are the focal points, or the foci that we were talking about earlier. Right, from there, you're going to divide between the focal points and the center into 4 equal distances. And then from the focal point and each of these points, you're going to draw different circle radii. So you'll see there, the first one is actually, you're going to measure from, I believe, from F1 to F. Let's see how they do it. So A to 1, right? And then you take that radius of A to 1 and you put it on F1. All right, and you draw those arcs with that radius of A1. Right, and then you go on and you'll measure A2 after. Right, so I guess you can there. So you see now he's measuring A2 and you put it on the same focal point. So now you have a circle or arc of radius A2 and you draw those arcs. And then you just continue to do the same. So then you'll measure A3 and put that circle or that radii of A3 on the focal point of F1 and draw a radius. And then wherever those lines end up intersecting, those become the points of your ellipse, and you just join the lines, right? Like that. So that is the intersecting arc method. I don't know, this intersecting line method is a little more, it's like a rectangular method as well as well. Look at it here. Very long video. Let me see. So this method, I believe, is also called the rectangle method. So you draw a rectangle and you divide it up into lines and let's see. And so the best thing really is to practice these someday, but we don't need to practice this right now, right? I just focus on understanding what it is, right? So the intersecting line method is the same thing as the rectangular method. I just want to show you what it looks like in the end. The person doesn't even finish it. Let me just go through it. Right, it basically looks something like this. All right. You're like dividing up these lines and just drawing points. It's gonna look confusing right now. Let's not waste too much time on that. I feel like I already wasting enough time on this question. Number 12, Caleb. Oh, you'll hear me.
I guess this one I put
Okay.
B.
You put B and Daniel.
12. I put A.
All right, so which is what how to bisect a straight line. So the answer should be A, right? So So Caleb, we would have kind of mentioned this last class. Remember when you're dividing a line, what you're doing is you're drawing, so say this is your line. If you want to bisect it, what you usually do is you draw a circle. So let me say this is the point. This is going to be the center of the circle, and this is going to be the center of the other circle. You draw, what you're going to do is you're going to draw a circle with that point being the center. So that there. All right, so it should be bigger than half the length of this the line. All right. Let's say I have that. Let's just pretend as the center, right? I'm gonna try and line it up as much as I can. And then you have the same circle. Let's see, can I copy this? Is there a copy tool? No. Anyways, let's just pretend it's the same size circle here, right? All right. And wherever those two circles intersect, that's going to give you a bisector, right? So that's essentially what's going on here. They just kind of trimmed off the rest of the circle. You can see this curve here is the same as this curve here. And this curve is that curve. So anyway, you see those curves, that means that those are arcs. So those are intersecting arcs or intersecting circles, right? Remember, arc is just a section of a circle, right? So that's how you bisect a straight line. Okay, so number 13, Daniel.
I put B.
Okay, then.
Don't know if that's right.
For 13, I put B as well.
Okay, wow, good job. You seem to be doing good at guessing. All right, so 13 is B. So the locus of a point is a point which moves on a circle or on an arc that just basically traces the path. So the locus of a point. So for example, let me see. Locus on a point of so I mean, yeah, just think of I could probably find a YouTube video. I'm not sure if it's that. All right, so locus of a point is basically a point that, you know, for instance, there's a point on this circle. That point just traces the path. So that point, there's a better video for this thing. Anyway, it's just a point that traces a path. All right. So for instance, I want a cycloid. Let me show you one on a cycloid. All right, so I'm just gonna all right, just try and think of this. Let's think of this circle as a wheel or a tire on a car, right? Pretend you have like a tack. Pretend like you have a tack or a screw or a nail or something in your wheel at this point on the wheel. As this wheel moves this way, so say a car moving forward, your wheel going this way. This point is going to continue moving, right? So as this circle continues to move along this path, this point is going to make this path, this kind of path, this line, and how it travels. So it's going to come here, it's going to come down, and then it's going to continue. It's going to continue on that path, right? So as that wheel keeps moving, this point here is going to go like that, and then it's going to go like that again, and it just keep going like that, essentially, right? So that's what our locus of a point is. It's basically a point that traces a path. Okay, so let's move on to the next one. As I said, the more we do these questions, the more these things will become clearer to you. All right. Question 13. Caleb? No, that was 13.
Yes,
Sorry,
I want
14.
14.
14. Yeah.
14 is A.
Daniel?
I put D.
So it says that best described in equilateral. So equilateral triangle means all the sides and angles are equal. Right, so 14, the answer is A. Right, so next page now, you'll set up to do this one, right? So yeah, let's look on this page, let me know when you're finished.
Cool. I'm done that page.
Okay, Daniel, how
Yeah,
about you?
same.
Yeah, okay, cool. So, is it 15 A? I mean, sorry, 15, Daniel, we put 15.
I put C.
And Caleb,
I put C as well.
all right, so you all know what this is then? Oh, you'll just guess
Um,
that.
No, I just guessed.
Just kind
I just
of,
remember that the tangent connects the two circles, but then I didn't know.
yeah, so an internal tangent essentially is a tangent that these let me see if you're correct. I believe you're correct. Yeah, so C, right? So let me show you. So internal tangent. There's different types of tangents, right? So there's internal and there's external tangent. So internal tangent just means that you have this instance where the two tangents cross like that, which is what you had in the answer. External tangent is the tangents don't cross, right? So you have the internal and you have the external. Right, so good guess. I mean, I think that's is a lot to do with just comprehending internal. You would think.
Wait, well, why wouldn't it be D? D is
Well,
the same thing.
yeah, but I mean, the difference here is I think it's kind of like they wanted to give the answer that best shows it, I guess. Because this one shows the
Okay.
external as well. So
Yeah.
if I was to look at this, how would I know which one is the internal if I didn't know the meaning internal? Because they have an external one here as well. All right, so
Okay.
it's usually a case of which one is the best answer. All right, so that's why I see. So Daniel, we go for 16.
C. Trapezium.
And Caleb.
Yeah, I put C as well.
All right, so a quadrilateral, well, yeah, the answer is C, right? With one pair of parallel sides is a trapezium. Right, so what is a quadrilateral with two pairs of parallel sides called? Right, so you see a trapezium, we need this and this, a parallel.
Parallelogram.
Okay, is that correct, Daniel?
Yeah, I think so.
Yeah, so I mean that is correct, but you also be careful, right? Because so a parallelogram, you have two parallel lines, but a square also has two parallel, right? Same with a rectangle. So I mean, you ain't gonna get that question in the exam, but just kind of try to trick you, right? That's parallel too. So a parallelogram is not the only quadrilateral that could be parallel. Anyways, I just thought I'd clear up for you. Number 17, Caleb.
Number 17, I put 45 degrees.
So angle EFH. Daniel, what you put?
I put D.
So the answer is 90 degrees. So what you need to be careful is whenever you see an angle written out like this, the angle you're usually looking for is the letter in the middle. So the F. So the F in this case is a 90 degree. And the key to knowing why this is, I mean, you can kind of look at it and see it's 90 degree. But you could also, let me show you. So this is what you call a tangent, right? You all understand what a tangent was. You'll show me that you understand that is. But a tangent touching the point of a circle is usually perpendicular to the radius of a circle, which in this case would be normal. So tangent on circle. So when you have a tangent, it touches the point of a circle that is perpendicular to the radius or the diameter of the circle. So remember, perpendicular means 90 degrees. So that's the kind of clue here, right? This line here is perpendicular to the radius, which means it has to be 90 degrees. All right, so number 18, Caleb. Number 18.
Yeah, I put A.
And Daniel.
I put B.
So 18, the answer is A. All right, so given a point P on the circumference of a circle, which of the diagrams below best demonstrates the principle of constructing a tangent to a circle to a given point? So you all haven't really done constructing tangents yet. But yeah, I mean, basically, the key is the word constructing. So they want to show constructed method. So let's read through this. Let's try and compare. So given a point P on the circumference, so P has to be on the circumference. So all of them do have P on the circumference. So all of them would work in that point. On the circumference circle, which should iron best demonstrates the principle of constructing a tangent to a circle. 3 points. Let me see, are they all tangents? I mean, they're all. Alright, demonstrates principle. Alright, so let's see if I can show you the method of constructing a tangent. This might take a little time. I might want to skip this question. Let me see. Let's watch this video. I think all you're doing is you're finding that point and then you're bisecting it, right? So, let me see. Let's see what he does here. Right, so he draws a circle. So it's not a bisector. Well, technically he is gonna bisect it. He drew these 2 points because this line is technically there's no promise that this point is in the center of this line. So what he's doing is from the center, he's drawing 2 radii of a circle. So this is one radius, and this is the next radius. Right? So this now is an equal distance. Right? So now he's doing the same the construction method of doing a bisector. Remember, you're drawing a circle on the end of the line. So consider this as the line now, not this full one. Right? Consider between here and here the line. So he's drawing an arc there and drawing the same radius arc on that side. And then wherever those intersect, I mean, he's going to do below here as well, just to be sure. Right? Wherever those lines intersect, that's going to give you your bisector. Right? And that is how you draw the tangent to a point P on a circle. Right? So that's what went on here. You see that X? As I said, that X is kind of, even though it's small, that X is 2 curves, 2 arcs. Right? So that's why the answer is A. All right, let's move on to this next page.
Yeah, I'm done. You know.
Okay, how would you kill him?
I'm on the last one.
All right. Okay, yeah.
All right, I'm done.
All right, so question 19, sorry, Caleb, for 19.
19, I put B.
Daniel.
I put C.
Okay, so the answer here is B. Is a hypotenuse and one angle. So, I mean, let's see. What's the best way to describe this way? So, a hypotenuse is the line that is like opposite to the 90-degree angle. So, the kind of key here, sometimes you have to kind of look for hints in these answers, right? So, the key here is to look at that this is a right angle triangle. And you could see that they draw a circle with an arc of basically the diameter of, but AC being the diameter of the arc. So if you were to like put this as the center point, you'd realize this arc here, and then drawing it the best, is the diameter of this circle here. So what that means is they gave this distance. Seeing that you could measure, seeing that you can draw this arc, seeing that they have drawn this arc, I should say. That means we were given this distance, which is the hypotenuse. So that's a kind of clue there. And then the angle they seem to have given us was the right angle, right? So I'll spend more time I'll do a class where we do constructed methods of triangle. It would make sense to kind of brush through this, but sometimes the key here is to kind of look for clues if you don't know, right? But as I said, all these questions are going to repeat. So if you see this, you would probably know the answer when you see it again. All right, so let's move on to the other one. Daniel, waiting for 20.
For 20, I put B.
B
I
and
kind of guessed.
Caleb.
You know.
I put I put B as well.
Right, so for the answer for 20 is B, correct. So in the figure above, A, B, C, D, E, F, regular hexagon. Hexagon is 6 sides. What is the value of angle X? So as you can see in a hexagon, this angle is the same as the angle on the inside, which is just going to be 360 degrees divided by 6 sides, right? Which is 60 degrees. All right, so let's move on to 21. Caleb.
Sure, I guess this one I put A.
Wait, but sorry.
A.
A and Daniel.
I put B.
Okay. So good guess, Caleb. So the diagram of ABCD is a parallelogram. The triangle CDE is going to be equal to half of ABCD. So this is a concept, I should say, a concept that would come a lot from these multiple choice. It won't be exactly in this format, but I'm gonna teach you something, right? So if you have anytime you have, so we're gonna have these two parallel lines, right? We're gonna have these two parallel lines. Let's say this is A and let's say this is B, right? All right, let's say this is A and this is B, right? When you have a rectangle within this, so let me draw this. Let's say we have a rectangle with length AB, right? And the height being whatever this height is, right? Anytime you have that, the same height and the same length, let's say for instance, let's say I did a parallelogram in it. Let me do it on a different color. If I did a parallelogram in here, right? So the height is the same. The height is the same and the length is the same. So what that means is that these two, the rectangle and the parallelogram, will have the same area because the formula for the area of a rectangle or a square is, the side by the side. So that would be length by the height, right? So these are both the same. So now you have to think, what is the area? What's the formula? Let me see this another color. What is the formula for area of a triangle? Caleb, you can tell me.
I forgot.
So the area of a triangle is half the base times the height. Right, so let's just change this to base just for the purpose of this question. Right, so the base is AB. Right, so if my triangle now has the same base, right? If it has the same height, then what is that going to mean? It's not going to mean, if it has the same base and the same height, it means that the area of this triangle is going to be half the area of the rectangle, because this is the same as this, right? If the base and the height is the same, the area of the triangle is going to be equal to half the area of the rectangle. You'll see what I'm saying there, right? You'll understand? Because I'm going to show another step to this. So there will be more questions similar to this, but the other questions, this meeting going to end in a minute. So let me try and rush it through quick. There will be another question where they would have twice the height here, right? So they would have a triangle that's like this. So it has the same base and it has twice the height. So what happens if it has twice the height? If the triangle has twice the height, if the triangle has twice the height as the rectangle, that would mean the areas are the same. So obviously, if our area of the triangle is half the area of the rectangle, then the area of the triangle with twice the height would be the same area as the rectangle. You understand what I mean? Let me know if you all understand, right? You all understand?